All right, here we go. What you guys just described to me is called line symmetry. There's two other types of symmetry, which I'll go over in a second. But just a quick recap of line symmetry. You can draw a line in and fold the figure over, and they match right up. So you see the happy face. Can we draw the line of symmetry in for that one? A vertical line, right? If I try to draw a horizontal line in, no good. How about the heart? Horizontal, yep. Any other lines? Because it could have more than one. Any other lines? All right, what about I have no idea what that is, but that figure? Is there more than one? Is there a vertical? Horizontal? Any others? All right, yeah. Nice job, guys. All right, I'll tell you this is an equilateral triangle. All right, so it's equilateral. Where's my line of symmetry or lines of symmetry here? All sides are the same length. What's up, Claudia? Okay, there you go. Almost do like an angle bisector from each of the vertices. Yep. All right, time to show off. Letters in the alphabet that have line symmetry. All right, there we go. Here we go. Up, and then everyone, yep, there's always that one student who goes right to the O. Yep. I'm not arguing about the humps. I'm not arguing about it. And then I think I heard somebody M. Okay, I think we're good here. Somebody say Z? Where? Yeah, I think Z's out, right? Z's out. All right. Hey, everyone showed off with their letters. How about some words? How about some words now? Mom. Now, be careful. How are you going to tell me? Because if I write out mom, no. Where's your line of symmetry? Okay, so you want to go here? Okay, I was thinking maybe you would want to do it. You can write it like that. Okay. Any other words? Bob? Yeah, good one, good one, good one. You guys are really stretching the English language here, huh, Bella? But I need to spell it going like this, right? Okay, next. Billy. Momo. That's yo-yo. That's like an actual thing. Yo-yo. Anybody want to go bigger than 3 here? Race car? No, that's just forward and backwards, though, right? I wouldn't be able to draw a line through. Yeah. That's all I've got to say. Come at me with a stronger game. Come at me with the stronger game. I've used that one for like the last 10 years, so yeah. Darn right it is. What? Did you just see the word I just wrote up here? 9. Let me know when you get something bigger than 9. All right. All good with line symmetry. All right, now, new to you now. New to you type of symmetry. Point symmetry. Basically, take a figure, turn it upside down, it's the same figure. That's point symmetry. All right, 180 degrees, it can be rotated, and it's the same figure. 180 degrees. Bottom line, turn upside down, and it's the same figure. Okay? It can be rotated 100, not less than, exactly 180, and it's the same figure back. So, ready? If I tell you that's a square, does that have point symmetry? Turn it upside down, is it still a square? Yep. How about this triangle? Does that triangle have point symmetry? No, why not? Go ahead, rotate it 180. It's pointing down now. All right, so that does not. And then how about the circle? Yes. All right, before I get to the last type of symmetry, O's taken. Get out of here. Letters that have point symmetry. Would C be? Turn it upside down? What do we think? No? Because it would be going the other way, right? E? How? Wouldn't it be going the other direction, right? It's going to the right now, but if I turn it upside down, it's going to the left. Now, let's bring in our boy, the Z there. Is Z going to work? Draw it on your paper, turn it upside down, you still get the same Z? I believe so. S? Does S work? If you turn it upside down, I still think you get an S. Oh boy, Jack. We all good? Everyone good? What do I have in store for you? You're wondering. Monday? Now, no swims on Monday. Point symmetry, right? Good? It's got point symmetry, flip it upside down, still the same sign, right? All right, good? Line symmetry, point symmetry, you can flip it upside down. One last symmetry, and that is rotational symmetry. All right, rotational. Read the definition real quick here with me. A figure is its own image, so it can carry it onto itself, but some rotation ready of 180 or less. So either you can flip it upside down or you can go less than that, and I still get that figure back. All right, I could still get that figure back. So 180 or less. So let's go to this. What's this figure right here? 6 sides? hexagon, and I'm going to tell you it's regular, meaning all the sides are equal. Does this have rotational symmetry? Can I rotate this 180 or less and get this same thing back? Yes, I can. All right. And I'm not going to stop there. Can you tell me the minimum number of degrees I could rotate in and get it back? Because a lot of you are like, oh, I turn my paper around, I get that same back. It's 180. But there's a smaller degree measure I could rotate it and still get that hexagon back. And how do I find that degree? That's what I want to know from you guys now. How do I find that degree measure that I can rotate it and still get that hexagon back? Yes, Thomas. That would give me 30, and it's more than 30, though. You sure you want to take 180? Because if I go all the way around, how many degrees am I going? I'm going 360, right? And now answer this question for me. How many times could I turn it, get that hexagon back before I got to the beginning again? So I want to turn it, I get the hexagon back. Turn it again, hexagon back. How many times would I get the hexagon back until I got to the beginning? 6, the number of sides, or the number of vertices. So I take 360 divided by 6, and that tells me I could go, like some of you told me at the beginning, I heard you, 60 degrees every time. All right, next one. I'm going to tell you this is equilateral. Does it have rotational symmetry? You guys, hey, remember, it's just not upside down. I get it. It doesn't have point symmetry because when I turn it upside down, it's not the same triangle. But could I go less than 180? Yes. Ready? 360. How many times could I turn it to get this same triangle back before I got to the beginning? 3, the number of vertices. So do I get something less than 180? I get 120 degrees. All right, so yes, this does have rotational symmetry. What about this bad boy here? I'm not saying it's equilateral. Go ahead, turn, ready? Keep turning your paper till you turn it upside down. Do you see that same thing back? No, either do I. So it does not have rotational symmetry. Ooh, how about our look, I don't know, a little block figure here? Does that have rotational symmetry? I'm hearing yeses and I'm hearing no's. Okay, hey, easy test. Ready? Let's see. Do I get it back? 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 When do I finally get it back? At 180, and that's okay because it's 180 or less. All right, so this is a yes because it's 180 degrees that I can get that figure back as long as it's 180 or less. Questions here? All right, I'm going to put vocabulary to the numbers we just found. All right, ready? You can go to the next page. I don't care. I'm going to stay here, though. What was that 6 and the 3? Okay, I had number of sides, but it was also the number of times what? You can turn it and get it back before you're at the beginning. That is what I'm going to refer to, and it's on your paper, as the order of symmetry. The order. How many times you can turn it before you get that figure, before you start from the beginning again. Okay, 6 and 3. The 60 and the 120, that's what we're going to call the magnitude. That's the smallest amount of degrees you could rotate to get that figure back. The smallest. All right? So the order is how many times you could turn it and see that figure back before you got to the beginning. And the magnitude is the smallest degree measure that we could get, all right, to get that figure back. All right, so going back, I know some of these are going to be repeats, but I had no choice. Down on part A, assume it's regular. All right, I'm going to go actual numbers here now instead of just calling out. Here we go. 4. Does this have rotational symmetry? Yep, it's a regular hexagon. Yep, okay. What would its magnitude be? Because it says state the order of the magnitude and the, state the order and the magnitude. So the order, which is how many times can I rotate this and get this figure back before I get to the beginning? 6 times. Everyone all right? Order 6. And yes, you can say, oh, it's the number of sides, but that's not going to work in a couple problems. And what's the magnitude? Here we go. 20, what's the magnitude? Do we have a 20? AKA, what's the minimum number of degrees I can rotate, Claudia, before I get it back? How do you get it? You take 360 and divide by 360 and divide by the order, 6, and you get 60 degrees. All right, does this right triangle have rotational symmetry? Does this right triangle have rotational symmetry? Here you go, 5, rotational symmetry. Remember, 180 or less. Do you get that same right triangle back? Nope. So this has no rotational symmetry. Are we okay on that? Keep turning it till you get to 180. You're never going to see it going this way. And then C, I don't know, ribbon, banner, flag, whatever you want to call it. Does it have rotational symmetry? Oh, whoa. I hear a couple of yeses in the crowd. All right. Here's what I was talking about. Now, when I ask for the order, you can't just count out how many sides. How many times can I turn this and see this figure before I get back to the beginning? That's what I want to know. How many times? I can see it twice, right? Everyone agree? Once at 180 and then once again at the end. So twice, I can see it. Meaning, what's the smallest degree measure I can rotate it and see it back? 17? 180. 360 divided by 2, 180. Everybody good? Take a quick breather because we're done with the symmetry part. I need to go. We're going on to a little different direction next. So take a quick breather. All right, good breather. Now, going back to reflections. The only thing I've asked you to reflect over is a line now. So far, everyone agree? Y-axis, x-axis, x equals 2, y equals 3, y equals x. Now I want to reflect through a point. Can we do it? Reflect through a point instead of a line. So go ahead, everyone. Set up triangle art, A-R-T. Bandcamp, good luck. Go get them. Just make sure you guys figure out how to rotate through a point. Play strong, take no prisoners. I don't know. What do you want? I don't know what to say. Make sure you stretch. All right, here we go. Everyone's got ART drawn. I'm going to reflect it through 4-1, this point right here, 4-1. Thoughts? Just go, right? What, Billy? So how far is it from point A, my point of reflection? 2, right? So I go 2 on the other side. Yep. Distance doesn't change in a reflection, so there's A prime. R prime's good, right? 1, 2, 3, 4. 1, 2, 3, 4. Nice, I like it. Ooh, and then we get to T. I know you know where to put T based on A and R, but what if all the points were just like T? How would I try to find out where they go? Okay, I want a big boy, big girl word for what you just said. Not bad. No. You were translated is fine. Up and over, rise over run. Slope. That's what you're doing, right? All right, so go ahead. Down and over, how many? From T to the point of reflection. Where are we going, guys? Down 2 over 4. So from that point, go down 2 over 1, 2, 3, 4. So you can use slope. You can use slope to find the images when you reflect through a point. Because I could tell you it's probably not going to be easy as counting from R to R prime and A to A prime. You're going to probably have points like all like T. So just use the slope, down and over, down and over. And then the last one here, and then you guys can get going on the assignment. Find me the point I reflected through. So graph both the original triangle ABC and the prime triangle. And we'll talk about the point of reflection. Did I graph this wrong? Okay. Well, that's because I'm looking at the top problem for your papers. One job. All right, point of reflection. All right, it's like I know you could just take a look at AA prime. It's the sucker in the middle. Big deal. All right, but ready? Let's say they're all like C and C prime, where you just can't count and go right in the middle of them. How could I find the point of reflection if all my points are like C and C prime? Ready? Count. Count over and down. How many units? Ready? Count with me. So I go 1, 2, 3, 4, 5, 6, 7, 8. And I go down 1, 2, 3, 4 units. So you're telling I go here 8, down 4. How could I go to the point in the middle, Julia? So instead, I'm going to go down 2 instead. And look where I end up. 1, 2, 3, 4, down 2, point of reflection. I'm going to challenge you before I let you go. There's another way I could do this. If you didn't want to count over and down and cut it in half. Okay, ready? Anybody know what this point represents if I connected A and A prime? If I connected C and C prime? If I connected B and B prime? The line of reflection is the same thing as the midpoint. All right, so if you want to make a little note of that, line of reflection is equal to the midpoint if you'd rather do the midpoint formula. All right, so you guys got a couple places you can go now. You got the book work and the packet work. 3-day weekend here to get it done, and you got 10 minutes, 12 minutes to get it started.